Okay, that video finished quickly, so we move on and let's have a look at the notes now. So this is, I think, the second or third last page of the notes, and we just want to have a quick look through what we've just been talking about. Okay, so there's the coin that we were talking about. Okay, and we have our lithium-7 here. We have our proton coming in, hitting it, and we have our two alphas being emitted, and our energy. So it's quite nice, right? So let's move on here. Okay, so Cochran-Walton. So we're going to mark it anyway because we're going to have it done. Bombarded lithium with artificially accelerated protons. Okay, it's fine. Following reaction took place. So we've our lithium-7 plus the proton giving it two alphas. You can see now how important it is to know these protons and these alphas. They're coming up all over the place. So H11, He24. Gain in energy. No. Okay, so there was a gain in energy. Now, if there's a gain in energy, there could be a bomb, could explode, but there's no net gain, because most protons missed the nucleus because the atom is basically empty space. So most of the protons missed, but the protons that hit, for those there was a gain in energy. So it's no net gain in energy, but there is for each time there's a collision, there is a gain in energy. First transmutation, changing an atom from one element to another using artificially accelerated particles, and that's important. So it's the first transmutation using artificially accelerated particles. Right? It verified E is equal to mc squared, Einstein's equation, and Walton got the Nobel Prize for his work in 1951. We might as well just write that in there. Okay, so that's what happened. There are the results. So the procedure. Okay, so look over. We can look at both. Protons produce in a hydrogen discharge tube. Protons are accelerated using the high voltages. Okay, so 400,000 volts. Okay, protons struck a lithium target. Alpha particles emitted in opposite directions, two alphas in opposite directions at the same speed. Therefore, momentum is conserved. We'll come back to that. Detected as flashes on a zinc sulfide screen. Okay, we might mark here, it's not on it, that these are zinc sulfide screens. Okay. Now, regarding the momentum, nothing to worry too much about, but if you think about it, the only particle moving at the beginning is a proton, and that's not moving in the x direction, in the horizontal direction. It's not moving in the horizontal direction. So in the horizontal direction, or the x direction, there is no momentum before, because no particle is moving that direction. So afterwards, from the principle of conservation of momentum, in the x direction, there must be no momentum again. So if you have two particles being emitted, they both will have momentum. So if one particle goes to the right, the other will have to go to the left at the same speed, so they'll have the same momentum and they'll cancel. So let's say if the momentum was 6, plus 6 on the right, minus 6 on the left, total is 0. So that's what that means there. And that's why it was set up at 45 degrees. Lithium target, put it in at 45 degrees to beam. Okay. And that's it. That's Cochran-Walton's experiment. So, watched a few clips following it, and we're done for the day. Thanks a minute.